Dissociation constant. Acid dissociation constant. Dissociation of weak acid in water. H plus aqueous is equivalent to H3O plus aqueous. For example, HCN dissociates in water liquid will produce H3O plus aqueous and Cn minus aqueous. So this equation can also be written as HCN aqueous means this HCN dissociate in water, aqueous means in presence of water, producing H plus aqueous, H plus in presence of water, so H plus is equivalent to H3O plus Cn minus aqueous. So the expression of acid dissociation constant can be written as H3O plus concentration or H plus concentration. Both are accepted. Ka or Kb value can be used to distinguish the relative acidity strength of weak acid and weak base. So the value of Ka or Kb can be related with the acidity strength of weak acid and weak base. The higher the value of Ka means the value of pKa is lower. Thus, the concentration of H plus is higher, pH value is lower. It means when you have higher value of Ka, lower value pKa, it is more acidic. Higher value of Kb means lower value of pKb. Higher value of concentration of OH minus, the pH is higher means it is more basic. For example, this acid, ethanoic acid with pKa value 4.74 and methanoic acid pKa value 3.76. So the pKa value of methanoic is lower than pKa value of ethanoic. So when the value of pKa is lower means the Ka value is higher in HCOOH. Ka value lower means lower pH, means this is more acidic. The methanoic acid is more acidic than ethanoic acid. The pKb value of C6H5 NH2 is higher than the pKb value of NH3. Means the lower the pKb, the higher the concentration of OH minus. Means this NH3 is more basic than C6H5 NH2. Autoionization of water. Water dissociates into ion very slightly in an equilibrium, or it is called self-ionization. So water ionized into H3O plus OH minus. We know that water is amphoteric, so it ionized into H3O plus and OH minus. Or you can write down as 1H2 only. It will be ionized into H plus and OH minus. So this is the value of Kw constant, ion product constant for water, written as Kw. Concentration of H3O plus times concentration of OH minus equal to 1 times 10 to the power of negative 14 at room temperature. Means in pure water, the concentration of H3O plus is equal to the concentration of OH minus. So that's why water, pure water is neutral. So the value of H3O plus and the value of OH minus in pure water is equal to 1 times 10 to the power of negative 7 molar. So this value is fixed in pure water. This Kw constant value is fixed for water at pH 7. A change in concentration of H3O plus causes an inverse change in OH minus concentration. So the higher the H3O plus causes lower hydroxide ion concentration. Lower H3O plus causes lower OH minus concentration. This means in acidic solution, H3O plus concentration must be higher than the concentration of OH minus. In basic solution, the concentration of H3O plus is lower than the concentration of OH minus, and in neutral solution, H3O plus concentration is equal to OH minus concentration. pH is a measure of the concentration of H plus or H3O plus ions in a solution. This is the equation to calculate pH. pH equal negative log concentration H plus. For POH, it's a measure of the concentration of OH minus ions in a solution. So POH equal to negative log concentration of OH minus. In neutral solution, pH is equal to 7, means H3O plus concentration equal to the concentration of OH minus. In acidic solution, pH is less than 7. It means that concentration of H3O plus is greater than OH minus concentration. In basic solution, the pH is greater than 7, means H3O plus concentration is lower than the concentration of OH minus. So pH scale, pH equal negative log H3O plus, POH equal negative log OH minus. H3O plus concentration equal to 10 to the power of negative pH, or it can be written as anti-log negative pH. Means the higher the concentration of H3O plus, the lower the pH value. The higher the concentration of OH minus, the lower the POH value. But we can only calculate the pH from this equation. We know that pKW equal pH plus POH equal to 14. How do we get 14? KW is equal to concentration of H3O plus times the concentration of OH minus, and KW has a fixed value. So when we have KW, we can have the value of pKW equal to 14. So the concentration here, pH plus POH, is equal to 14. Example, in art restoration project, a conservator prepares copper plate etching solutions by diluting concentrated nitric acid to 0.0063 molar. Calculate the concentration of H3O plus, calculate the pH, concentration of OH minus, and the value of POH of solution at room temperature. First, you have to identify the type of acid. HNO3, nitric acid, is a strong acid. Strong acid dissociates completely in water, means the initial concentration 0.0063 molar, final concentration 0, because it dissociates completely, means all HNO3 will be converted to H3O plus and NO3 minus. So concentration of HNO3 plus will be 0.0063. Finally, and then the pH is equal to negative log H3O plus, and you will get 2.2 pH value. Next, we need to calculate the OH minus concentration and POH. We know that pKW is equal to pH plus POH. Value of pKW is 14. So POH equal 14 minus pH. We have the pH value 2.2. So our POH is 11.8. The concentration of OH minus is anti-log POH. So anti-log negative POH equal to 1.6 times 10 to the power of negative 12 molar. This is the concentration of OH minus. degree of dissociation is the ability of acids or bases to ionize or dissociate in aqueous solution. Concentration of acid or base dissociated. So this is, we look at the change of concentration of acid and base over initial concentration of acid or base. So it depends on the question whether it's calculate the acid or the base. Percentage of dissociation is acid concentration or base concentration dissociated. This is the change in concentration over initial concentration of acid or the initial concentration of base times 100, because we want the percentage. Magnitude of Ka for weak acid. Higher H3O plus means larger Ka value, means it's more acidic. So we know that pKa equal negative log Ka. Weak acid has more Ka. So the concentration of acid initial minus the concentration of acid dissociated is almost the same of the concentration of acid initial, because the change in concentration, the acid dissociated is very small. The value or the concentration of acid dissociated for weak acid, because we know for strong acid it does dissociate completely, but for weak acid it is very slightly dissociated. So it means the change or the acid dissociated concentration is very small. That's why if you take the initial concentration minus the value or concentration of the acid dissociated, is almost the same as the value of initial concentration of the acid. Concentration of acid initial minus acid dissociated, we know this value is very small because weak acid dissociated very slightly in water, so this value is very small, equal to the concentration of acid initial. Example, what is the pH of 0.5 molar HF solution at room temperature? So we know that HF is weak acid, given the value of Ka equals 7.1 times 10 to the power of negative 4. So you have to construct ice table. We want to know the X value. So HF weak acid does not dissociate completely. It dissociates very slightly. Initial concentration of weak acid HF 0.5 molar, and then initially that there are no products at all, 0. Change in concentration, this concentration will be decreased, so negative X because 1 mole. These two concentration will be increased, positive X because 1 mole. Equilibrium concentration, 0.5 minus X, this is 0 plus X, 0 plus X. So we have the Ka equal concentration of H3O plus times concentration of F minus over concentration of HF. Ignore H2O because it's in liquid state. We don't put liquid or solid state in the K expression. So in equilibrium, this is X, so X squared over HF 0.5 minus X equal to the Ka value given. So we know that this X value is very small because weak acid dissociated very slightly, so this X value very small. Assumption 0.5 minus X, knowing that X is very small, almost equal to 0.5 because X is negligible because it's very small. So we know that Ka equal x squared over 0.5, because 0.5 minus x is equal to 0.5. So we put 0.5 here, equal to the Ka value, and you will get x value 0.019. So 0.019 here, if you want to check whether it's very, very small or it cannot be assumed as very small, this is how you check the value of x. So that value x over 0.5, you times by 100 and you'll get 3.8%. As long as the percentage is less than 5, so the assumption is justified. It means it is true that the x value is extremely small. As long as it's less than 5%, so this assumption is accepted. So this is how you check the assumption. Next, so we know our x is 0.019 molar. That's the concentration of H3O+, because here at equilibrium H3O+ is x. Our x is 0.019 molar. So pH equal negative log 0.019 and the pH 1.72. This is the final answer. Next, calculate the percent dissociation of 0.5 molar benzoic acid given the value of Ka 6.3 times 10 to the power of negative 5. First, our benzoic acid is weak acid. For weak acid, this acid dissociates very slightly in water. So it will not produce 0.05 product. It will produce a very small amount of product only because benzoic acid is weak acid. So now we have at equilibrium 0.25 minus x, change in concentration is negative x because 1 mole. So plus x, 1 mole, this one plus x because 1 mole. Initially, there are no concentration of the product. So at equilibrium, benzoic acid concentration 0.25 minus x, H3O plus concentration x, C6H5COO minus concentration is x. So write down the Ka expression, products over reactant equal x squared over 0.25 minus x. So we know that x is very small, so Ka equal x squared over 0.25 only, because we assume it's very small. So Ka equal x squared over 0.25. So we'll get x value 4 times 10 to the power of negative 3. Now we want to check the assumption, whether it is true that the x value is extremely small or not. So you take that x value over 0.25 times by 100 and we'll get 1.6%. This value is less than 5%. So assumption justified means it's correct that the x value is extremely small. Carry on with the concentration of H3O plus equal to x. So we have our x value 4 times 10 to the power of negative 3 molar. Percent ionization is ionization acid dissociated. It's the value of x. So this is it, 4 times 10 to the power of negative 3 over initial concentration. Our initial concentration 0.25 times 100, you'll get 1.6%. This is how much the benzoic acid dissociated in water. Base dissociation constant, Kb. Look at the dissociation of weak base in water. So it can be written as, the Kb expression can be written as BH plus times OH minus over B. For this equation, B plus H2O. And for NH3 plus H2O, you'll get the product NH4 plus OH minus the product over reactant NH4 plus concentration times OH minus over NH3. ignore H2O, ignore H2O because it is in liquid form. Don't put state of matter, liquid or solid in the expression. Higher OH minus concentration means larger Kb value, means it is more acidic. So pKb equal negative log Kb. Example, dimethylamine is a key intermediate in detergent manufacture. It has a Kb value of 5.9 times 10 power of negative 4. What is the pH of 1.5 molar CH32NH? CH32NH is a weak base. Weak base slightly dissociate in water, very slightly dissociate in water, so you have to construct the ice table. Initially, there are no concentration of the product, so change in concentration, negative X, positive X, positive X, and then at equilibrium 1.5 minus X, here is 0 plus X, 0 plus X at equilibrium. And then Kb expression, the product over reactant, concentration CH32NH2 plus times concentration OH minus over CH32NH concentration equal X squared over 1.5 minus X. Given the Kb value, so that is equal to 5.9 times 10 power of negative 4. So we assume that X is very small. 1.5 minus X is equal to 1.5. So you get the X value 0.0297. So we check whether it is extremely small or not. So you put this X value over 1.5 times 100, it is 2%, less than 5%. So the assumption justified, it is correct that X is extremely small. Next, we have the value of X. We know that the concentration of OH minus is X. We have the value of X, 0.0297. We need to find the pH, but from OH minus, we need the POH value first. So POH equal negative log OH minus, negative log 0.0297. The POH value is 1.53. pH is equal to 14 minus 1.53 and the pH value is 12.47.